Perhaps a radio signal detected from Proxima
Yes,
Centauri.
Scientists predict that the James Webb Space Telescope will be more powerful than any human-launched space camera and will open up hitherto unattainable opportunities for mankind to investigate distant objects. In order to determine whether Proxima b emits artificial light, the James Webb Space Telescope will observe it in space. Scientists want to know if the lights coming from Proxima b are from other planets, so they're using spacecraft like New Horizons and Voyager 1. A significant discovery regarding artificial lights on Proxima b by the James Webb Space Telescope has the potential to alter everything. Although it is more difficult to detect sentient life outside of Earth, there may be multiple universes where it can be found. Using the James Webb Space Telescope, researchers are examining Proxima b, a planet that has produced some surprising results. The stars seem brilliant at night, according to the telescope, but since they are so far away from our solar system, we might not be able to see the planets that orbit them. Certain exoplanets might have the necessary elements for life, indicating that extraterrestrial life exists there. Proxima b is one of 3 Alpha Centauri stars that share a same gravity center. It is unclear to scientists whether Proxima Centauri is passing by or circling the other 2 stars. Proxima Centauri, the 3rd brightest star in the sky, is thought to be the result of the combined efforts of all 3 stars. It is challenging to notice Proxima Centauri with the unaided eye since it is smaller and less brilliant than the other 2 stars. It orbits its parent star, which makes up roughly 5% of the distance between Earth and the Sun, on a short course of 4.6 million miles. Proxima Centauri may not have always been habitable if it had formed along the present course, according to astronomers, and exploring it may take thousands of years. Due to their difficulties in visibility, exoplanets like Proxima Centauri are hard to locate, and scientists have to use their imagination to determine their existence. Many of the trillions of exoplanets in our galaxy, according to EXPs, are roughly the size of Earth. During its 4-day orbit around its parent star, a hot gas giant half the size of Jupiter was discovered in 1995. Exoplanets are located using the wobble method, which monitors the radial velocity of stars. Exoplanets can be discovered using transit detection, which makes use of the Kepler telescope. Kepler searched for tiny light spots, drops produced by planets passing in front of them, in a region of the sky that had 150,000 stars. One can calculate the planet's size by looking at the guiding star. Another technique for finding exoplanets is spectroscopy. Researchers can examine the light that stars emit after passing through asteroids to learn more about the composition of the atmosphere. Various techniques are employed in the search for exoplanets, including gravitational microlensing. The huge telescope known as JWST was launched at the end of the previous year for $10 billion. A substantial increase above its original $1 billion budget. 4 instruments on the telescope allow it to clearly detect infrared emissions. The spaceship bus that holds the James Webb Space Telescope also houses its computers, engines, and communication systems. A large sun cover and a cryocooler that uses helium to chill its components to -236 degrees Celsius, 3,393 dF, are features of the bus. Folded and sent into space, the James Webb Space Telescope solar shield was unable to be supported by the launch rocket. During the first 2 weeks of the observatory's trip, the solar screen opens out to the length of a tennis court. Its 5 layers of Captain E polymer serve as a sun shield, preventing heat and sunlight from entering the telescope. The transit method is used by the James Webb Space Telescope to search for extraterrestrial life by collecting direct images of exoplanets near bright stars. The James Webb Space Telescope allows scientists to study the weather, vegetation, color changes, and color of these exoplanets. The Allen Telescope Array, which consists of 42 radio antennas, is used by SETI scientists to look for signals from the 20,000 nearby red dwarf stars. This is related to the search for extraterrestrial life since even the tiniest microbes on far-off planets may emit chemical signals that are detectable by powerful telescopes. Researchers are always searching for novel gases or compounds, such as water, in an attempt to discover life, but they must exercise caution because these substances might not be related to living beings at all, and might even have entirely unrelated sources and processes. Our closest companion, Proxima b, was found in 2016 and is encircled by planets that orbit it similarly to our Sun. Because it lies in the habitable zone of its star, it may have liquid water and life, and its mass is similar to that of Earth. From a scientific point of view, Proxima b might have liquid water and be a rocky world like Earth. Proxima b orbits a star, which is similar to our solar system, but not as bright or big as our Sun. The exoplanet is tidally locked and spins at the same speed as its star, meaning that in both light and dark, one side is always facing the star, and the other side is always facing away. The exploration of Proxima b could ultimately teach us more about the conditions that make a planet habitable and bring us closer to answering the age-old question: Are we alone in the universe? The building blocks of Proxima b, a planet near its star, are thought to be carbon dioxide, water, rock, and clouds. Its surface temperature is between minus 130 and 86 degrees Fahrenheit, or minus 90 and 30 degrees Celsius. Proxima Centauri b resembles Earth more than previously believed and is 177% larger than Earth. Like the Moon and Earth, it has dark and bright sides as it revolves around its star every 11.2 days. Because of their distance from Earth, the two additional planets in the system of 3 stars that the planet circles are more difficult to analyze. The Goldilocks zones surrounding Earth and Proxima Centauri b are places where life may yet exist. About 2/3 of Earth's energy comes from Proxima Centauri b, which orbits its star a 1/12 as far away from its sun as Earth. Astronomers have discovered that Proxima Centauri b has been hit by 60 times more high-energy radiation than Earth, and between 7 and 16 times more than Earth. It may have lost about an ocean's worth of water in the first 100 to 200 million years after its formation. Scientists believe that Proxima b could keep most of its atmosphere and liquid water on the surface, making it habitable. A steady flow of strong radiation from its host star might help Proxima b's unlikely life form grow on the day side. A group led by Harvard scientist A.I. Loeb suggested using the James Webb telescope to find LED light on Proxima b. They found that the telescope can pick up 5% of the power from stars coming from LEDs. If James Webb Space Telescope can find narrow band light like LED candles, it could describe the planet's atmosphere. Researchers can use observatory tools to study energy movement and light curves. The James Webb Space Telescope Exposure Time Tool helps astronomers predict potential artificial light sources. The James Webb Space Telescope will also develop artificial lighting using regular lasers that are 500 times brighter than those on Earth. The Breakthrough Starshot program aimed to send robots to Alpha Center if a spacecraft flew 20 times faster than light. The program began with a strange sound from the 64 M Parkes radio telescope in Australia, which was being used by astronomers to pick up radio waves from Proxima Center's strong flares. The $100 million project Breakthrough Listen, led by Andrew Simeon from Berkeley and funded by Internet Yuri Milner, began in 2015 and allowed radio telescopes more time to look for advanced civilizations. Space scientists used Parkes to look at the STA for 26 hours as part of their study of stellar flares. Teenage student and SETI programmer Shane Smith found a sharp narrow band emission at 982.551, which was given the new name Breakthrough Listen Candidate 1. Parkes caught the signal 5 times over several days, each time with the telescope aimed directly at Proxima Centauri. Breakthrough Listen separates signals from deep space from signals from Earth and satellites flying around the Earth, a concept not seen before. Andrew Simeon, head of a team, revealed that a high-frequency radio wave passed some tests due to certain factors, but did not explain why. Simeon suggested that the radio wave's focus could be due to a quirk in plasma physics. Jason Wright, a scientist at Penn State University, believes that the signal may be from technology from other planets, not Earth.